Good morning, everyone. Let us start our course CMOS analog VLSI design. In past 3 decades, CMOS technology has rapidly embraced the field of analog integrated circuits, providing low cost, high performance solution and rising to dominate the market. While silicon bipolar and compound semiconductor technology find niche applications, only CMOS processes have emerged as a viable choice for the integration of today's complex mixed signal systems. Analog circuit design itself has evolved with the technology as well. High voltage, high power analog circuits containing a few tens of transistors and processing small continuous time signals have gradually been replaced by low voltage, low power systems comprising thousands of devices and processing large, mostly discrete time signals. For example, many analog techniques used only 10 years ago have been abandoned because they do not lend themselves to low voltage operations. In the early 1980s, there are many experts who predicted the demise of analog circuits. Digital signal processing algorithms were becoming increasingly more powerful, while advances in integrated circuit technology provided compact, efficient implementation of these algorithms in the silicon. Particularly, VLSI industry is moving from large designs to the smaller scale, small, compact designs. Many functions that had traditionally been realized in analog form were now easily performed in the digital domain, suggesting that with enough capability in IC fabrication, all processing of signals would eventually occur digitally. The future looked quite bleak to the analog designers. But now, if you look at the VLSI industry today, analog designers are in great demand. So why is it like this? After all, digital signal processing and IC technologies have advanced tremendously in last 3-4 decades, making it possible to realize processors containing millions of transistors and performing billions of operations per second. While many types of signal processing have indeed moved to the digital domain, analog circuits have proved fundamentally necessary in many of today's complex high performance systems. If you consider digital circuitry, every year cost per function decreases roughly by 29%, while if you consider analog circuits, cost per function still it does not scale so well. There are many complaints about analog circuits. For example, supply voltage is too low, device gain is too low, it's not significant. There is a horrible matching between the components. For example, we need to design differential configuration, so transistors should match and they don't match. Does it mean that analog will die and everything will be digital? Do you agree with me? Let us try to find out. How we design a system nowadays? There is something called as analog signal processing. You can call it as a signal conditioning. There is an analog to digital converter, and there is a digital signal processing. And finally, you get the output, which is in a digital form, and then you apply it to the system. Nowadays, trend is to reduce the processing done in the analog domain and more towards the digital domain. So today's trend is more and more towards DSP side. If you see the analog market, analog chip sells in billions of dollars. Every year there is more than 10% growth in the analog market. If you see the job requirement, there is a crunch of analog chip designers. People are saying that pure analog design is over. What does it mean? If you would like to be a good engineer, then your portfolio should look like digital plus analog. Is it not true? Let us find out. This diagram indicates the today's modern analog system. There is a continuous time, continuous amplitude, real-time signal. Let us say, for example, you picked up an ECG signal. It's a very small signal. It is continuous in time. It is continuous in amplitude. You require sensors to pick this signal and to convert this physical quantity into an electrical quantity. Then you need interface electronics for signal conditioning. For example, a to D converter. Then you get the digital data. So you process it using DSP. So now your data is discrete in time and discrete in amplitude. Now you again use interface electronics. For example, digital to analog converter. You apply it to the actuators, and finally you get continuous time, continuous amplitude signal. So you start from continuous time, continuous amplitude signal, and finally in real life you deliver what is called as continuous time, continuous amplitude signal, because real life understands only continuous time and continuous amplitude signals. So we'll come back to this slide afterwards. Now what is signal and what is noise? If this is a picture given to you, can you identify what is the signal and what is the noise? Is it noise? Not necessary. Is it a signal? Not necessary. It could be a signal containing a noise. So now you require an electronic circuit which will process this, and it will extract the signal from this information. Is it possible that this kind of signal you will get in real life? Yes. For example, if you pick up any signal related to, for example, neuromorphic signal or a muscle signal, EMG signal, then its amplitude will be very small and it will look like a noise, but there is a signal. You will have to separate it out. So you require the analog circuits. Now let us consider a eggshell analogy which is given by Paul Gray. So you process the signals digitally, which is at the core of your system. However, you need sensors, actuators to connect your digital system to the real life system. You require images, you require displays, you require audio IOs, you require a storage media, you require a transmission media. So that means outside this shell there is a real life, and the real life talks in terms of only analog signals. Thus, even though your digital domain is very large, to interface this digital domain with the analog, you require interface electronics. And even though this is a very small contribution in an entire system, but it is very critical. Now let us consider this green board. There is a receiver and there is a transmitter, and in between there are a lot of interconnects, thousands of interconnects. So the output is taken at the transmitter end, then it goes to the receiver, and that information receiver processes. Now you just plot the eye diagram at the output of the transmitter and at the input of the receiver side. So this bottom figure shows the eye diagram at the output of the transmitter side and at the input of the receiver side. Is there any difference between these two? Yes. At the output of the transmitter, since eyes are widely open, you can easily say whether the transmitted bit is 1 or 0. But same is not true at the receiving end. Since eyes are not widely open, you cannot say that the received bit is 1 or 0. What does it mean? It means that the signals which you are transmitted were digital, and now at the receiving end those signals are not remaining digital. Now it has become analog. So at the receiving end you require circuitry which will process or which will consider these signals as analog, and then it will carry out the processing. We all know that naturally occurring signals are analog, at least at a microscopic level. A high quality microphone picking up the sound waves of an orchestra generates a voltage whose amplitude may vary from few microvolts to hundreds of millivolts. The photocell in a video camera produces a current that is as low as few electrons per microsecond. A seismographic sensor has an output voltage ranging from few microvolts for very small vibrations of the earth to hundreds of millivolts for very heavy earthquakes. Since all of these signals must eventually undergo extensive processing in the digital domain, we observe that each of these systems consists of an ADC and a DSP, as shown in the topmost figure. The design of ADCs for high speed, high precision and low power dissipation is one of the many difficult challenges in analog domain. In practice, the electrical version of natural signals may be prohibitively small for direct digitization by the ADC. The signals are also often accompanied by unwanted out-of-band interferers. Thus, we need to modify the topmost figure. So we require an amplifier to boost the signal level and an analog filters to suppress the out-of-band components. So the design of high performance amplifiers and filters is also a topic of active research for the analog designers. Now let us consider another example of digital communication. So binary data generated by various systems must often be transmitted over long distances. For example, computer networks in large office buildings may transmit the data over cables that are hundreds of meters long. What happens if a high-speed stream of binary data travels through a long cable? As illustrated in this figure, the signal experiences both attenuation and distortion. It no longer resembles a digital waveform. In short, the data which you are transmitted was digital through a lossy cable, and now it has been transformed into the output signal which is analog. Thus, a receiver similar to an analog circuitry is required to extract the information. In order to improve the quality of communication, you may incorporate different mechanisms. For example, multi-level signals rather than binary signals, which is shown in this figure. So it is a 4-level data system. Every 2 consecutive bits in the sequence are grouped and converted to one of the 4 levels. Then each level is twice as long as a bit period, demanding only half the bandwidth required for transmission of binary stream. This kind of multi-level signal system is extensively used in today's communication systems. What it necessitates? Now it becomes a necessity to have DAC in the transmitter to produce multiple levels from the grouped binary data, and also an ADC in the receiver to determine which level has been transmitted. The key point here is that increasing the number of levels relaxes the bandwidth requirements, while it also demands a higher precision in the DAC and ADC. So it is whose job? It is the analog designer's job to design ADCs and DACs with high precision levels. Another example is disk drive electronics. The data stored magnetically on a computer hard disk is in the binary form, which is shown in this figure. However, when the data is read by magnetic head and converted to an electrical signal, the results appear as shown in the figure. The amplitude is only a few millivolts. The noise content is quite high and the bits experience substantial distortion. Thus, we need to amplify the signal, filter it, and then digitize for further processing. Depending on the overall system architecture, the analog filter in this case may in fact serve to remove significant portion of noise and distortion of the signal. The design of each of these building blocks poses a great challenge as the speed of computers and their data storage media continues to increase every day. Then another example is of wireless communication. The signal picked up by an antenna of RF receiver exhibits an amplitude of only a few microvolts and a center frequency lies in a gigahertz. Furthermore, the signal is accompanied by large interferers. The receiver must therefore amplify the low level signal with minimal noise and operate at a high frequency and also withstand large unwanted components. Please note that these requirements are necessary even if the desired signal is not in analog form. The trade-offs between noise, frequency of operation, tolerance of interferers, power dissipation, and cost constitute the principal challenges in today's wireless industry. Now consider another example of optical communication. For transmission of high-speed data over very long distances, cables generally prove inadequate because of their limited bandwidth and considerable attenuation. Thus, as illustrated in this figure, the data is converted to light by means of a laser diode and transmitted over an optical cable which exhibits an extremely wide band and a very low loss. At the receiver end, the light is converted to a small electrical current by photodiode. The receiver then must process a low level signal at very high speed, requiring low noise bandwidth circuit design. Now let us consider another example of sensors. Mechanical, electrical and optical sensors play a critical role in our lives. For example, video cameras incorporate an array of photodiodes to convert an image to current, and ultrasound systems use an acoustic sensor to generate a voltage proportional to the amplitude of the ultrasound waveform. Thus, amplification, filtering, and A to D conversion are essential functions in these applications. These are examples of the sensors which shows an accelerometer employed in automobiles to activate the airbags. When the vehicle hits an obstacle, the drop in the speed is measured as the acceleration, and if exceeding a certain threshold, it triggers the airbag release mechanism. So modern accelerometers are based on variable capacitor consisting of fixed plate and a deflectable plate. The deflection and hence the value of the capacitor are proportional to acceleration, requiring a circuit that accurately measures the changes in the capacitor. The design of such interface circuits is quite difficult because of typical accelerations. The interpret capacitance may change by less than 1%, demanding a high precision in the measurement. Thus, we require analog designers who can design this kind of sensors and who can measure the small deflection in the deflectable plate. We can use some other methods, for example, a differential kind of a configuration, which is shown in the next figure. Then let us consider microprocessors and memories. Today's microprocessors and memories draw upon a great deal of analog design expertise. You may consider that microprocessors and memories process digital information and they don't require any analog circuits. While it is not true, there are many issues related to the distribution and timing of data and clocks across a large chip. It mandates high-speed signals to be viewed as analog waveforms. Furthermore, there are a lot of non-idealities in the signal and power interconnects on the chip, as well as package parasitics. Thus, it requires a solid understanding of analog design. In addition, memories also have sense amplifiers. So the design of sense amplifiers necessitate an analog technique, application of an analog technique. For these reasons, it is often said that high-speed digital design is in fact an analog design. So what are basic building blocks in any analog design course? In analog design course, what you study primarily is resistors, capacitors, current meters, differential amplifiers, transconductance amplifiers, operational amplifiers. Then there are a lot of issues of layouts in the analog circuits. So what you primarily study is how to match the resistors, how to match the capacitors, and how to match the transistors, for example in current meter, and then how to simulate the analog circuits. This is what is your entire course. So basically you require ADCs, you require DACs, you require amplifiers for amplification, you require signal processing circuits which will process signals at high frequencies, you require power management circuits, for example voltage references, voltage regulators, you require oscillators, you require PLL. This is an example of a chip picked up from the reference that is shown. Can you identify in this chip where are the analog blocks required? There are voltage regulators. Yes. There is an image area which is in VGA format. There are ADCs. There are timing generator circuits, IO circuits. So there are a lot of analog circuits in this chip. This is another micrograph of a particular die. Can you identify where are the analog circuits? Yes. There are biasing networks. There is a power amplifier. There are transmitters. There is a receiver. There is a biasing circuit. There is a control circuit. There is a synthesizer. So there are multi analog circuits in this micrograph. This is a embedded DRAM, 16 MB embedded DRAM. Can you identify where are the analog circuits? Yes, there are input outputs. There are decoders, row decoders, column decoders. There is a VPP pump circuitry, and there are sense amplifiers. And you can see that 1088 sense amplifiers are used in this chip. So these are our analog circuits. This is another example. It shows the MEMS pressure sensor. So if it is a MEMS pressure sensor, you need an instrumentation to measure the difference in the pressure. So what kind of configuration is used? It's a Wheatstone bridge. So it's an analog circuitry. You require a high precision, accurate amplifier differential configuration to measure the small changes in the pressure. So it's a job of an analog designer. Then let us consider MEMS sensors, for example cantilevers. So these are the cantilevers implemented for measuring the difference in the pressure applied. There is a displacement, so you require an analog circuitry which will measure the small displacement. So it's a job of analog designer to design an instrumentation circuitry. This is another interesting application called as neuromorphic circuit. neuromorphic circuits, they mimic the behavior of the neuron. So the way our body reacts, circuit also reacts. So there is entirely a different domain called as neuromorphic engineering, wherein engineers they design the electronic circuits which mimic the behavior of our neurons. So it's an entirely analog domain because behavior of the neuron is not a digital. Like your brain does not function in terms of ones and zeros. It produces analog signals. So you need analog circuits to mimic their behavior. This is called as a neuromorphic circuit. It's a very big domain. This is an example of a neuromorphic circuit, and it's called as an inhibitory synapse. Then there are many applications in real life wherein you require analog circuits. For example, avionics. There are a lot of biomedical applications like implantable pacemakers, cardioverter defibrillators, like cancer radiotherapy related equipments. All they employ the analog circuits. Even your internet core routers also need the analog circuits. In short, this is what is the nanoscale design, and where analog circuit fits everywhere. So you can carry out the research in any of these domains. For example, you can design analog circuits based on the carbon nanotubes. You can design the analog circuits for wireless communication. You can do the modeling of the analog circuits. You can do the verification and testing of analog circuits. You can operate the analog circuits in low power domain, so you can study the subthreshold behavior of these analog circuits. You can study the leakages into these analog circuits. You can study novel microarchitectures. You can use novel devices. So it's a very challenging and very good domain. There are a lot of opportunities available in this domain. Nowadays, if you study any system, it's not remaining only digital or it's not only analog. Entire thing is mixed. For example, you want to design an airbag system. Now this shows the block diagram of an airbag system, which has been picked up from one of the IEEE transactions paper. What it shows you that it's not only analog or digital, but in fact there are multiple disciplines that are incorporated into this. Like there's a mechanical, there's a thermal, there are signal graphs, there's an optical domain, there's an electrical domain, there's a digital domain. Thus, as an engineer, you cannot say that I know only analog design and I am not conversant with the analog part. I know only optical design and I am not conversant with the, for example, mechanical part like accelerometers. I don't know how to sense the signals. I don't know how to process the signals in analog domain. So it's a multidisciplinary system and we need analog designers. Now what are the qualities that any analog engineer should have? I would say that the first and the foremost important quality is he should be a creative person. If there are problems which are easy problems, so they are already solved problems. So who requires a creative solution? So if there is a tough problem, that requires a creative solution. We need a person who can deal with the changes, because technology is changing very rapidly, particularly MOS technology. So we require the persons who can understand this technology and who can use this technology into the analog domain. And it's a fun. Human beings are already creative persons, so why not to study this? However, one must understand the differences between integrated circuits and the discrete circuits. If you come with the background of the discrete circuits and then you study the CMOS analog VLSI design, then it may be difficult for you. So I would recommend that some of the concepts which you have studied, particularly in the courses which deal with the bipolar technology, you please preempt them, and then in a fresh mind you study the analog integrated circuits. For example, there is no concept of backgate bias, there is no concept of substrate coupling, there is no concept of channel length modulation in discretes. We don't even discuss those points. However, these concepts are very important when you study analog design, which is a VLSI based circuit design. So how do you proceed? You must do significant background research, like an explorer who finds out each and everything before carrying out an exploration. Then you must do the brainstorming sessions, find out various options available. Once you get a lot of options, then you must work like a judge, choose a particular solution, and then finally once you get the solution, then you must proceed it and you must implement that design like a warrior. So you need to do a good background research, you need to find out multiple options available to you, you need to choose a particular solution, and then you need to implement the design. In short, the objective of this course is to teach you the analog integrated circuit design using CMOS technology. Thus, some specifications will be given to you. You need to brainstorm it and finally come up with a circuitry which has a lot of MOS transistors. What is the course philosophy? It's not like a digital design. It's not like I sit on a computer, I write some code, then if I find an error, I simply go on debugging it till I get the correct solution. That would be a risky path. Thus, a proper path or a wiser path to an analog IC designer is that take a pen, paper, try to understand how the circuits work. Once you understand how the circuits work, then you go back to the computer, do the simulations, find out the performance. If it is not satisfactory, you can any point of time come back and rethink where is the problem. So the wiser path is not doing the simulations directly on the computer. First you try to understand the circuits and their behavior. So what are basic prerequisites for this circuit design? First is you should be in a position to do the mesh analysis properly. Like KVL you will have to apply. You should be in a position to do the nodal analysis like KCL at each node. So you should know the concepts of what do I mean by linear circuit, what do I mean by independent voltage source, what do I mean by voltage controlled voltage source, current controlled voltage source, voltage controlled current source, what are the characteristics and ideal operational amplifier. I am particularly talking about ideal operational amplifier because we have a separate chapter on operational amplifier wherein we will discuss in detail about the other op-amp parameters. Then circuits containing various capacitors, various inductors you need to analyze. For example, we are going to study oscillators, so then you require the L, C. Then you need to know what do I mean by Laplace transform, how do I analyze the linear circuits, how do I find out the stability. Then you should be in a position to do the frequency as well as time domain analysis. Then you should be in a position to plot the Bode plots. You should be in a position to understand the Bode plots, and then finally you should be in a position to use various circuit simulators. If you are comfortable in all these domains, then I don't think it will be difficult for you. Some of the points which I would say will make your job easier if you understand them at this point of time. Like for example, knowing the analysis is necessary, it is not sufficient for the designer. Look at the multiple ways when you design a particular blocks. Don't think that this is the only solution available. There may be multiple solutions of the same problem. It is an unfortunate, but it is true that sometimes you will have to use trial and error approaches in the analog circuit design. Approximations are sometimes good. Rather than doing the full-blown analysis and then coming to a conclusion that, oh, this intuitive thinking could have given me the similar answer with a negligible deviation, then why not to approximate the circuits? Thus, in analog circuits, most of the time we do the approximations. Carry out an intuitive thinking before applying the full-blown analysis. For example, look at the circuitry and try to find out what is the gain. Just draw the small signal model and try to find out the gain rather than applying the full-blown analysis. Don't every time try to solve each and every problem from the scratch. Try to relate the problems with the problems which you have already solved. Every time ask one question to yourself: why is this? Why is this like this? Rather than asking what it is. Be curious to find out the output of the circuits. Keep your mind open. Don't close it that this is the only solution possible. No, there may be another solution possible. And thoroughness is very important. What do I mean by thoroughness? Let us say you design a circuitry for low power and then you come up with the solution. So don't you think there are other trade-offs? Yes, there may be other trade-offs. So when you come up with the one solution, also report the other trade-offs that are there. What does it mean? Does it mean that analog design is very difficult? Let us try to find out. Yes, it is, because of the following reasons. Number one is that it has a multi-dimensional trade-off. What do I mean by multi-dimensional trade-off? If you study the digital circuits, there is a trade-off between speed, power and area. However, in analog circuits it is not true. There are multiple parameters which trade with each other. In short, we will see those parameters. Then, analog circuits are very sensitive to noise, crosstalk and other interferers. Then there is more influence of second order effects. You cannot simply ignore each and every time second order effects. For example, channel length modulation or bulk effect, backgas bias effect, you will have to consider. Unfortunately, analog circuits are rarely automated. Usually, we handcraft each and every device in an analog circuit. There are a lot of difficulties in modeling and simulation of analog circuits. Results are primarily analyzed based on an experience. Digital mainstream IC technologies do not easily lend themselves to the analog design. Analog design requires novel circuits and architectures to achieve the high performance. Thus, there are many problems, there are issues. Like analog design have multidimensional trade-off, they are sensitive to noise, crosstalk and other interference. There is a more influence of second order effects. They are rarely automated. Each and every device you need to handcraft. There are a lot of difficulties in modeling and simulation. Digital technologies will not easily adopt the analog design. So there is a problem with the fab. Then there is a problem with the performance. To achieve a high performance, you simply cannot scale down the circuits. You need to have an alternate solutions, like you need to find out the novel circuits, novel devices, novel architectures. That analog design is difficult. Now this octagon, it shows the trade-off that I have discussed right now. There is a multi-dimensional trade-off. Now what are the parameters that trade with each other? There are 8 parameters that trade with each other: noise, linearity, gain, supply voltage, voltage swings, speed, input output impedance and power dissipation. For example, you want high gain. If you want high gain, then that output impedance will also increase. If you want low power dissipation, then the swing will reduce. If you want to reduce the noise, then swing has to be increased. Then linearity, it trades with the speed. So in the entire course, we are anyway going to discuss all these parameters and how they trade with each other. Now I mentioned about linearity. Let us in short discuss at this point of time what do I mean by linear. So what do you think, what is linear output? You simply draw a straight line, and is it a linear? No. Now for example here, yt is the response of a particular system, or let us say an amplifier, and xt is the input. So there is an alpha 0 plus alpha 1 xt plus alpha 2 x square t plus and so on. So what you do is, I already said that you can apply the approximations, and there is nothing wrong in applying the approximations in analog circuits. So yt you can approximate as alpha 0 plus alpha 1 xt, where you can consider alpha 0 as an operating point or a bias point, and alpha 1 obviously will be small signal gain because you are multiplying it by xt, and that becomes the yt. So finally an amplifier has a response yt with bias point alpha 0, which is a DC, and a small signal gain of alpha 1. So you plot it, so it will look somewhat like this, shown in this response. Okay. So is it linear? No, it is not linear. Thus input output characteristics are non-linear. For linearity, your input output characteristics should pass through origin. If there is an input 0, then output should also be 0. That means if xt is 0, yt should be 0, which is not true in this case. Thus, if the slope of the characteristics, we can call it as an incremental gain, varies with the signal level, then the system is non-linear. Please remember that. If the slope of the characteristic varies with the signal level, then the system is non-linear. So now how to make the system linear, that we will study in a due course of time. In short, I would like to say that analog design is a very important domain. Your portfolio as an engineer will look good if you study digital as well as analog design. So in next lecture we'll start with the MOS fundamentals. Thank you very much.